Okay, everybody. So I'm going to go back to lecture 19 and cover one of the examples which we did not have time in class to do. So this example is unique compared to what we've done so far because it's a magnetic boundary condition problem. However, what makes it unique is that there's a surface current on the boundary. Previous examples, we did not have a surface current on the boundaries. So in this example, we have a plane which exists at y equals 0, and it separates two magnetic media. Medium 1 is when y is less than 0, has a relative permeability of 3. And medium 2, which is when y is greater than 0, has a relative permeability of 9. There's a sheet current which exists on the boundary, 1 divided by mu naught, in the AX direction, amps per meter, and it exists right there on that interface. We're given the field in the first medium, which is equal to 4AX plus 6 AZ. We have two objectives here. First is to find out what is the field on the second boundary, and then what angles do the field in the first boundary and the second boundary make with the normal to the surface. So we should notice that we have different angles because we have different permeabilities. Okay, so now I'm going to cover this example. So let's write down some information. Okay, so in this example, we should always write down what are the two media and what are the conditions upon the two. So I'll just abbreviate that as medium 1, okay? And that is when y is less than 0, okay? And that has a relative permeability, so mu sub R1, which is equal to 3, okay? We should also note that we do know what the field is, right, B1, which is equal to 4 in the AY direction plus 6 in the AZ direction. Okay, so we know the field in the y direction and in the z direction, okay? Let's also write down that we know where medium 2 is, and that is when y is greater than 0, okay? And it has a relative permeability which is equal to 9. Okay, now what we also have to use is that we have a surface current, which is 1 divided by the permeability of free space, and that's in the AX direction. Okay, we'll give it some units, amps per meter. Okay, now what we're to find is what is B2 equal to, okay? And then also, what are the angles that B1 and B2 make? So we'll call this theta 1. So that's the angle that B1 makes with the normal, and theta 2, and that's the angle that B2 makes with the normal, okay? So this is the problem that's stated. This is what we're trying to find. Okay, so as always, when we're doing problems which are based in physics, we always want to draw a picture of what's going on, okay? So what I'm going to do is I'm going to draw the boundary first, okay? And I'm going to draw the boundary current on the boundary. So you can see that there's a surface current in the x direction. So what I'm going to do is I'm going to draw the x direction coming at you, okay? So you'll have to remember that when we want to draw vectors coming at us and away from us, we draw them as circles, and we'll either use them as x's or with dots. So we're using dots, right, which means that that surface current is coming at you, okay? So that is K, right? And what I'm going to do is I'm going to have the y-axis going right and left, okay? So I will call this direction the plus y-axis, and we'll call this direction the minus y-axis, right? So at y equals 0, right in the middle here is where we have the separation of the boundary. And I will say that going up and down will be the minus z, and the plus z will be going up. And that's not so relevant for this problem. Okay, so what we have over here is boundary 1, so we'll give that mu sub r1. And here we have boundary 2, and we'll call that mu sub r2. Okay, so we have our picture drawn, and we kind of understand what things are going on in one area and trying to figure out what's going on in the other area. Okay, so what we always have to do for boundary condition problems is we have to determine what the normal and tangential components of a vector are to the boundary. Okay, so we can see that the boundary is y equals 0, right? So the normal direction would be pointing at a 90-degree angle from it. So you can see that there's two normals, right? There's the normal, which would be in the y direction, right? So we could draw a unit vector here and say there's the ay vector, right? And that is going to be normal. And we can also say that here's another normal here, which is the negative ay vector, okay? All right, so we can say that the y component is going to be the normal component, right? So if we look at our vector here for the first medium, we should see that it does have a y component, right? And that's going to be our normal component. And it's using the positive y direction, so we might as well call that our normal, okay? So I'm going to say that Bn1, right? The normal component of Bn is what's directed in the y direction, so we'll simply say it's equal to 4ay, right? And we should always note that a vector is made up of a tangential and a normal component, right? So whatever's left has to be the tangential component. So obviously 6az is going to be the tangential component. So we'll say bt1 is equal to 6az. Okay? And that makes sense, right? Because the one component is going to be normal to the surface. That'll be in the y direction. The other component will be going in the z direction along the boundary tangentially. All right, so once we know these, we can apply our boundary conditions. Now, usually I'll start with boundary condition 1 whenever there's no surface current. But when there is a surface current, I'll start with boundary condition 2 just because it's so much easier and we can get the result much quicker. So boundary condition, so I'll say BC number 2, right? And that simply says that the normal components for both vectors have to be equal to each other. So we already know what the normal component for B1 is, so we simply can say that Bn2 is going to be equal to that. So we'll just say that that's equal to 4ay. Okay? So the first thing we did is we found out what the normal component is.